You will hear tropical cyclones referred to differently depending on where you are at geographically on the planet. In the North American hemisphere, we use the term hurricane to describe a tropical cyclone. It's called a typhoon in Southeast Asia and that Western Pacific region. It's called a cyclone in countries that border the Indian Ocean, and a tropical cyclone in Australia. Aboriginal Australians have their own term for it. On the north coast of Australia, they call it a willy willy. But even though a tropical cyclone is named different things in different places, all of those names are talking about the same thing, a system that forms in a tropical air mass with a lot of heat and a lot of water. Tropical cyclones, or hurricanes, as I will probably slip up and call them a few times, have a few defining characteristics that make them very easy to identify. First is a calm eye, then an eye wall of heavy wind and rain, and separating rain bands. Winds are fastest in the eye wall and slowest in the eye, and the eye has the lowest pressure in the tropical cyclone. And I'll go over each of those features in a little more detail in just a few slides. This graphic shows the track of a storm in the Pacific Ocean. This is Typhoon Haiyan, which occurred in 2013. Haiyan was a super typhoon, one whose sustained winds are 130 miles per hour or greater. It was notable for being one of the strongest tropical cyclones ever to strike land. It had a very well-defined eye, an eye wall, and a rainband structure. Its maximum sustained wind speed was 195 miles per hour. It killed over 6,000 people, mostly in the Philippines. This is the type of event that could easily wipe out a small society. This graphic right here gives you an idea of how a hurricane actually functions. We're going to start from the middle and work our way outward. In the center of the storm here, you have an area of deep low pressure. It is air that is rising rapidly up from the surface of the planet because it is so warm and light. The rising air is loaded with water vapor that started out really hot, so the moisture content is extremely high. As it rises, it rapidly cools and condenses, and as it condenses, it releases a lot of latent heat, which helps supply even more lift, and that lift helps to support additional thunderstorm development. As this air reaches the top of the tropopause, it spreads outward due to that Coriolis force. It diverges, and then it begins to sink in different places. Some right in between the different created updrafts, which form the different rain bands, and some all the way out on the outskirts of the storm. What we're looking at here is Hurricane Florence that formed in the Atlantic in 2018. This is a really beautiful picture of a hurricane. You can see that clear, calm eye in the center. The sides of the eye are the eye wall, and then if you look, you can see like clear like stripes almost in the clouds coming out of the spiral out of the center of the eye. Those are the rain bands. There is something interesting I would like you to notice here. And first of all, I would like you to be able to look at this hurricane not knowing anything about it, including the fact that I just called it a hurricane, which kind of gives it away, and be able to tell me which hemisphere that occurred in. The northern hemisphere, because you can see that it is spinning counterclockwise. It is spinning inward towards the center, counterclockwise. Okay. And this brings up a really interesting phenomenon that occurs with hurricanes because of the fact that they are spinning and they have an eye. Let us suppose that you were standing with your back to an oncoming hurricane. As that hurricane approached you, because it's spinning, the winds would hit you from one side. As that eye passed over you, directly above you, all of a sudden there would be no wind at all. It would be very calm and clear, and you would think that the hurricane was over. But guess what? You haven't reached the other side yet. Once that eye totally passes over you, you will again experience very strong winds. Only this time they're going to be coming from the opposite direction. That's because while that hurricane is motivating forward, it is also spinning. Hurricane strength really depends on how much water vapor condenses to liquid. We call that the latent heat exchange. Notice that it is highlighted in red. This is how much of the water you are actually moving around. When latent heat is released into the storm, it creates a positive feedback. It just helps warm that air up more and more, and it provides more and more lift. More lifting leads to more cooling and more condensation, which releases more latent heat. Hurricanes must have warm seawater to persist. This is their fuel, and that is why they go away if they pass over land, or even if they pass over an area of cold water. This table outlines the stages of hurricane development and something called the Saffir-Simpson scale, which is how we categorize hurricane strength. We're going to start with hurricane or tropical cyclone development, and this occurs in 4 distinct stages. So here we go, stages of development. Initially, in its baby stage, a hurricane starts out as a small thunderstorm. At this point, we call it a tropical disturbance. A tropical disturbance generally has no major rotation, and it's just a disorganized cluster of thunderstorms. If this continues in the right kind of environmental conditions, which is basically over warm water of 80 degrees Fahrenheit or above, it can start to form a bit of rotation, and the winds will start to strengthen because the pressure gradient is getting stronger. This is stage 2, called a tropical depression. Then, if it continues to develop and get stronger rotation, it starts to really rain, we've reached stage 3, which we call a tropical storm. This is the point at which they will start assigning names to the storms. The wind speeds for it to be a full-fledged tropical storm have to be somewhere between 39 and 73 miles per hour. Once those winds hit 74 miles per hour, we call it a hurricane and we are off to the races. This is the point at which we start categorizing it. In the North Atlantic, we use the Saffir-Simpson scale, as I said. You see 4 categories displayed in this table, but there are actually 5. Category 5 is anything 155 miles per hour or above wind-wise. And damage-wise, we're talking full-scale catastrophe. We'll look at what a Category 5 damaging characteristic might be in just a little bit. But for reference, in 2017, when Hurricane Maria happened, it was passing through Puerto Rico, and the wind was so extreme with sustained winds of 185 miles per hour, gusting at 220 miles per hour. It was one of the fastest and most powerful hurricanes we've ever seen in the North Atlantic. After Maria, people began asking if there shouldn't be a Category 6. Category 5 winds at 156 miles per hour are going to destroy or at least severely damage any known structure that humans have built. Catastrophe, total destruction. If any of you are familiar with the acronym FUBAR, this is it. After events like Maria, another thing that people start asking is, can't we build structures that are a little more hurricane-proof, that can withstand these hurricane-force winds? Yes, possibly we could do that. There are instances of buildings that have withstood hurricane winds, but it would be crazy expensive, and you can't logistically afford to put up that many buildings everywhere that will keep people safe. Buildings capable of withstanding 230 mile per hour winds do not come cheap, so it's really not feasible to just take that tack that we can just build stronger buildings. Getting back to those categories in the Saffir-Simpson scale, they are based on wind speed. And again, in order for a hurricane to grow and to strengthen, it has to have a lot of warm water, preferably 80 degrees Fahrenheit or over. This is the best range for them. There also must be little to no wind shear. This is different than what you want, say, in thunderstorm development, where we want that wind shear. Remember that a thunderstorm develops from a single cell to a multi-cell with extra wind shear. We add a little more wind shear, we get a lot stronger thunderstorm development. Tornadoes thrive on wind shear. But a hurricane does not like that kind of environment because it's trying to rotate and gain as much momentum and as much latent heat exchange as it can get in order to grow. Wind shear stops that process and it essentially tears hurricanes apart. Here's another graphic showing you how a tropical disturbance can develop as it moves across what we refer to as the main development region of the North Atlantic. If the conditions are right, that little tropical disturbance can develop into a hurricane. So starting out, that single tropical disturbance, which may have formed off of an atmospheric wave that moved out of Africa, it may form into a tropical depression, and then into a tropical storm, and then into a hurricane. They don't all have to form right off of Africa, though. Some hurricanes will form all the way near the Caribbean Sea or even in the Gulf of Mexico. This slide's just showing you a few different ways that meteorologists can actually monitor hurricanes. We can do it with satellites, with ocean buoys, with Doppler radar, and then hurricane hunters can drop measuring devices called radiosondes into a hurricane from an aircraft to actually tell us what's going on inside that hurricane. Something that we can do with hurricanes that we cannot do with tornadoes. Hurricane hunter training is not nearly as extensive as you might imagine, but it does teach you how to survive in the harshest of environments and puts you through rigorous training underwater to try to attempt to mimic the survival of an aircraft going down in the ocean. Would that not inspire confidence in you if somebody told you that's what they were going to train you to do? Okay, and now for some hurricane geography. Hurricanes are restricted to tropical oceans, very important. And if they move into higher latitudes, they either go away or they turn into something else, which we will typically call like an extratropical cyclone. For example, Hurricane Sandy, which occurred in 2012. This was a hurricane that extratropically transitioned into a mid-latitude cyclone. It became a really bad storm that still caused a lot of damage. Subtropical highs guide hurricanes, and I'll show you what I mean in the next graphic, but subtropical highs tend to redirect hurricanes. So you'll see this sometimes that a hurricane is heading along a fairly straight course and then suddenly curves off to the right. That is because of the influence of the subtropical high. Also important to note, we typically do not get hurricanes within about 5 degrees latitude of the equator because of the Coriolis effect is basically nil there. It's not strong enough to sustain the hurricane's spin. This map is showing all the storms that we know to have happened since about 1851. There are some notable features here. First, let's talk about the Bermuda High, or the subtropical high, redirecting hurricanes. Remember that large-scale clockwise rotation that exists in the northern oceans and how that is caused by the influence of the subtropical high pressure? Look at that same rotation in a lot of these hurricane tracks. They tend to follow that general subtropical high. You're probably wondering what's going on in the South Atlantic. We have an almost complete lack of storms there. That is because the South Atlantic is generally far too cold and has too much wind shear to support hurricane development. We did get one, Hurricane Katrina, in 2004 because nature likes to surprise us every now and then. And in March of 2019, we also got Tropical Storm Iba, which just surprised the heck out of everyone. So every now and again, we do get conditions where it's warm enough for hurricanes to form in the South Atlantic. But if you will cast your eyes towards the Western Pacific, perhaps you've noticed that our biggest blob of red, which is those Category 5 strength events, this occurs in the Western Pacific. Western Pacific storms, typhoons, are the biggest and most intense tropical cyclones on the face of the planet, with the highest wind speeds. This is because the Pacific is massive and it has a lot of warm water on the other side of the ocean that helps to increase the intensity of these typhoons. Then note what's going on in the Indian Ocean. This is the part of the world where tropical cyclones are the deadliest. Why? because there are a lot of people that live there, and they live in very low-lying elevations along the Bay of Bengal. The bay itself is very shallow, and this promotes very high storm surge, which we will get to next. This leads to people being inundated or flooded very easily. There is a lot of information on this slide. However, I would like to draw your attention to the red boxes outlining a few of the callouts and the callouts contained within those boxes. Make sure you read these very carefully, because there is a very great likelihood, I would say a 99.9% likelihood, that you will be asked about the information contained within these highlighted boxes. Here we just have two examples of two hurricanes that existed in opposite hemispheres. Notice the spin. Remember that in the southern hemisphere, things rotate in the opposite direction. So Hurricane Catarina that made landfall in Brazil rotated clockwise, whereas Hurricane Gilbert in the North Atlantic rotated counterclockwise. In general, hurricanes are the main meteorological killer on our planet. Tornadoes can cause a horrendous amount of damage, but remember they are quite short-lived and they generally don't cover a whole lot of territory. Hurricanes, on the other hand, can persist on average 5 to 10 days, sometimes lasting up to 15 days as long as the environmental conditions are right. The coastal storm surge and flooding that's generated by tropical cyclones is typically the most dangerous aspect. Storm surge is when we actually see a rise in sea level that's caused by those strong winds that are associated with the hurricane. And it's storm surge. This is the major contributing factor to why tropical cyclones in the Indian Ocean can be so deadly, because of those low-lying coastal areas of India. For instance, the Bola cyclone of 1970 made landfall and killed 500,000 people in one night. Let me say that again. 500,000 people dead in one night. This region around the Indian Ocean, these people are particularly vulnerable to this inland flooding because they have so many people living right along that very low-lying coast, and poverty really makes evacuation difficult. This schematic just shows you how storm surge is created. If we take a hurricane and we move this system onshore, the amount of space between the bottom of the ocean and the actual base of the hurricane starts to shorten. That water has to go somewhere, and it goes up, and then it goes onto shore. Here's another view of that from NOAA, the National Oceanic and Atmospheric Administration, showing how storm surge is created. You might imagine that storm surge paired with a high tide and additional waves can make those heights extremely impressive. East U.S. during an El Nino episode. That is it for this lecture.